The dissolving of a solute in a solvent is an equilibrium process. We talked about this when we talked about the evaporation of a liquid. So let's say you put sodium chloride into some water. Initially, you have sodium chloride dissolving. You don't have any sodium chloride recrystallizing because there aren't any sodium and chloride ions in solution to recrystallize. But as this dissolution keeps going on, then the concentration of dissolved particles increases, and now we can have recrystallization happen. And so as you get more and more dissolved ions, the rate of recrystallization will increase. At some point, the rate of crystallization and dissolution is going to be equal, and we have a dynamic equilibrium. So we represent that with a double-headed arrow, showing that this is going in the forward direction. We've got sodium chloride dissolving, but we also have sodium ions and chloride ions combining to form solid sodium chloride. We have recrystallization. Here's pictures. So there's our lump of sodium chloride, and it's going to begin dissolving, but there's no sodium and chloride out here, so it can't recrystallize. As this dissolves and we get more and more sodium and chloride ions in the solution, the rate of recrystallization will increase. Eventually, this will become equal in rate, dissolution and recrystallization, and so we have a dynamic equilibrium. You've got salt sitting down here, but it's not a static situation where nothing's changing. Sodium ions are leaving, sodium ions are coming in. And so the shape of the crystal may change over time. In fact, it probably will. We'll get to that in a minute. A saturated solution is one where we have dissolved solute in dynamic equilibrium with solid solute. So there is the solid present, and there's also dissolved solute, and they are in equilibrium. If you add more solute, it's not going to dissolve. It's going to sit there in the bottom with the rest of the solid. So it's saturated. The solution is full. Remind me to show you a video at the end of class today. I forgot to do it yesterday.
Could you heat up certain solutions to be able to make them more soluble?
Yes. Solubility is temperature dependent, and so you can heat the solution and usually get more to dissolve.
Would you be able to do the opposite, freezing it, or like getting it colder?
If you get it cold, then most things are less soluble. And that's one of the reasons that when we've made solid precipitates as our product, sometimes we put that in an ice bath and before we filter it to reduce the solubility and to get more of our product out. And then when we rinse it, we use cold water instead of warm water because we don't want to dissolve our precipitates. And so, yeah, we definitely use temperature to control the solubility. An unsaturated solution is one that has less than the equilibrium amount. So in the process of dissolving and recrystallizing, you got to the point where all of it dissolved. And so it's all dissolved. If you add more of the solute, it will also dissolve. And so you can mess around with this at home. If you want to do this, though, just use a small amount of water because whether you want to use sugar or salt to dissolve in the water, they're both highly soluble. And so if you use like a big cup of water, it's going to require a lot of salt or sugar. Just take a little bit of water and add some sodium chloride, some salt, and stir it. It'll dissolve. Add some more. And you keep doing that until when you add it, it doesn't matter how long you stir it, it's not going to dissolve. That's a saturated solution. Until it becomes saturated, it's unsaturated. You put more in, it will dissolve.
So what was the point before it becomes saturated to be considered unsaturated?
Unsaturated, yeah.
Is like the ocean unsaturated? Or?
The ocean is unsaturated, yep. And then there's supersaturated. And that's the thing I'm heating up here.
So it's supersaturated?
Well, right now this is just saturated, right? Because there's solid. Now you can see there is water in there. It's not that this is melting. Oh, I probably shouldn't have stirred it like that. It's not that this is melting. It's that it's dissolving in the water. But there's still solid here. So right now this is a saturated solution. But I'm heating it up to get all of the solid to dissolve. Supersaturated solution contains more than the equilibrium amount of solute. It has more solute in it than can dissolve in that amount of solvent. That kind of seems impossible, doesn't it? In a way it is. It's an unstable situation. The easiest way to make a supersaturated solution is to take a saturated solution and heat it until it dissolves. You have a slightly unsaturated solution at an elevated temperature. If you allow that to cool undisturbed, you can kind of fake out the solution. It's a little bit like Wile E. Coyote running off the cliff, or Bugs Bunny, or any of those cartoon characters. They'd run off the cliff, right? Now, if we ran off a cliff, that first step off the cliff, we'd fall immediately, right? But cartoon characters don't fall until they notice that they're not on land anymore, right? You break all the laws of physics in cartoons. I think of a supersaturated solution as being a little bit like that cartoon character in midair. It'll stay there until it realizes, oh, wait a minute, I shouldn't be able to do this, and then everything crystallizes. What can cause that? Well, bumping it can cause that. Dropping a crystal in the solution can cause that. Scratching the side of the container. Do you remember when we did the melting point of sodium thiosulfate? And we had a supercooled, right? So you had it melted and then you cooled it down well below its melting point. And it was still a liquid. Then you dropped the crystal in and it began freezing and the temperature went up, right? Crazy.
So is there like a limit to how much you can supersaturate?
Yeah, there is a limit to how much you can supersaturate. And you can't easily make a supersaturated solution with just any substance. Some of them definitely are much easier. Sodium acetate is the classic one. Does it very nicely. Okay, so let's see what happens. So these are photographs, but it's more fun to watch a video. So here is the supersaturated solution, and they disturb it by touching it with a stirring rod. And then the crystals begin to form, and they keep forming until it gets to equilibrium.
Supersaturated, does it usually go back to its solid form? Or?
It will, when disturbed, it will crystallize out and return to a saturated solution.
So only the amount that was there after it was saturated would crystallize, or the whole thing? So there's liquid inside. So.
Yeah, so there is water in there, right? That solution looked solid because there's so much sodium acetate in there, but you can see when I tipped it, there is some water in there. It's just all stuck inside the crystals, and so it can't pour out. So it doesn't look the same as like sand sitting on the bottom of water. But it is just a solid in a liquid. It's not the same as the sodium thiosulfate where it was melted. That was just a melting. This is dissolving. So let's look at these videos. Oops. Okay, so that is saturated sodium acetate. And he sticks a stirring rod in, and you can see the crystals forming. Putting that stirring rod in there, or the spatula, gives the crystals a place to form. And once you get one crystal forming, then all the others form. They just need a place to form. This is fun with sodium acetate. So dipping toothpicks in there. They look like cotton balls and they're actually crystals. And the temperature goes up. So they're just sticking the thermometer in there. Oop, there it goes. You can touch your finger. It gets hot, but not burning hot. It seems solid, but the water is there. It's just trapped in all the crystals. So it's kind of like this slushy texture.
So are slushies like super saturated?
No, they're just partially
You could make
frozen.
them like that.
I don't think you could. This is fun
Can't you
making.
do that with water? You freeze it to a certain point.
You can get water to be super cooled. In fact, that's what happens with a can of soda that was in the freezer, and then you open it and it freezes. You're like, what the heck? It's cool how it just travels up into the beaker. Sometimes called hot ice because it looks like it's freezing. It resembles ice, and yet it gets warm as it does this. Yeah, she spelled it. Because it releases energy as the crystals form.
We're at Link. We wanted to show you how we created our amazing new web.
What?
It's crucial because when we look good online,
Oh, that's awesome. Go away. Okay, so we will have a live demonstration of that a little bit later. See how we're doing here. So now you can see that more of it is dissolving as I'm heating it up. We'll just continue letting that thing heat. The solubility of most solids increases when you heat them. So here we have solubility measured in grams of the solute in 100 grams of water. So looking at this table, if we look at the line here for sodium chloride, we see that at 0 degrees Celsius, looks like maybe 33, 34 grams of sodium chloride will dissolve in water at the freezing point of water. You increase the temperature, you get up to boiling water, and it's gone up to almost 40 grams. So the solubility has increased. The temperature dependence of the solubility of sodium chloride is very low. It doesn't change much. Some of the rest of these change a lot. Like calcium chloride goes up really high with temperature as the temperature increases. There's one of these where the solubility decreases as you heat it. Sodium sulfate becomes less soluble at high temperatures. That's weird. That's atypical. But this temperature dependence is why, as I'm heating this sodium acetate solution, it's dissolving now. Because as it gets warmer, the solubility increases. And so I will be able to dissolve all of that solid, and then we'll let it cool down to room temperature before we disturb it. So I mentioned earlier that in a saturated solution, over time, the shapes of the crystals might change because you have recrystallization and dissolving occurring. Recrystallization can be used to purify a solid. The digesting step that we did when we did that experiment where we did the digesting. Which one was that?
Isn't that what they do?
The Gooch Crucible one.
Ores, to like make gold or something, like to get rid of.
A little bit. You can heat gold and cool it and remove some of the impurities that way. With ionic compounds, you'd heat them. to cause them to dissolve and then let the crystals form very slowly. So you heat them up, get them all to dissolve, and then you let it cool very slowly. And as it cools slowly, as the ions come in and recrystallize, the crystalline structure rejects impurities. Maybe you're making sodium chloride and there's a calcium ion that tries to get in there. It doesn't fit well, and so it gets kicked out.
So when something's super saturated and you know you have to touch it, if you just let it cool down, will it just start forming?
It will not just start forming, otherwise it wouldn't be supersaturated.
Even if you like went right almost at freezing or something?
Well, you could do recrystallization with sodium acetate. You would need to give it something to a nucleation site so that it could crystallize slowly as it cooled.
So it wouldn't crystallize out, so.
Yeah.
The sodium acetate doesn't. Most things do. They don't form supersaturated solutions. When the supersaturated sodium acetate crystallizes, it does that very, very quickly, and so that's not going to reduce impurities. It will probably trap the impurities. This is a photograph of rock candy, which is just made by recrystallizing table sugar.
So it's just straight sugar.
It's just big crystals of sugar. Pure sugar. Yep. It's just a lot more fun to eat than a teaspoon of granulated sugar, right? That's no fun. It's kind of nasty, actually.
That's fun.
You can make this at home, but if you want to do that, find some instructions online, because if you don't do it right, it's not going to work. I tried it as a kid. Maybe I'll try it with my kids over break. That's one of those things I would do in my free time, but there never seems to be any free time. But recrystallization. Gases in water. So temperature affects the solubility of gases in a different way. So here we have cold soda and warm soda. We know from experience if the 2-liter bottle of soda is cold and you pour it, you get less foaming than if you've got warm soda and you pour it. This foams up a lot. The foaming is caused by the carbon dioxide coming out of solution. Carbon dioxide is more soluble in the cold soda than in the warm soda. So we observe that warm soda goes flat faster than cold soda. You could do this at home too. 2 glasses of soda. Put one in the fridge, leave one out on the counter. Come back a couple hours later. The one in the fridge will be fizzier than the one out on the counter that's warm. Oxygen levels are lower in warm lakes and rivers. So fish and other aquatic life depend on dissolved oxygen in the water to live. If the temperature of the water is warmer, the solubility of the oxygen is lower, and so there's not as much oxygen. So,
do they like frozen lake?
well, there are cold water fish and there are warm water or tropical fish. And they are adapted to living in their own environment. And so, in Minnesota, the lakes get a solid layer of ice at the top. It's so thick that they used to lay train tracks and drive locomotives and trains across the lake to bring the timber down. And so at that very cold temperature, oxygen is more soluble. And so cold water fish are used to higher levels of oxygen. Tropical fish are used to lower levels of oxygen. You put a cold water fish like a goldfish in a tropical fish tank, and you'll find it at the surface gasping, just because it can't breathe. It can't get enough oxygen. You can get thermal pollution in lakes and rivers. You get a factory, right? And it's doing some process that generates a lot of hot water, dumps the water in the river. Well, the water may be perfectly clean water, but because it's hot going into the river, that raises the temperature of the river, at least in that location, which reduces the oxygen levels and kills the fish. Thermal pollution.
There was one that caught on fire, wasn't there?
There was a river that caught on fire, yes. But that was due to, different flammable, non-soluble things on the surface. It's always bad news when your river catches fire. Pressure has a big effect on the solubility of a gas. So, can of soda, there's always going to be a head space here, a space where it looks like there's no soda, there's some sort of a gas there. That's actually CO2 under pressure. When you open the can, you get that familiar psst sound. That's the excess pressure escaping. And once you release that pressure, the soda begins to go flat. It takes it a while, but it starts to go flat.
So that's why there's excess pressure in the can
To keep the CO2 in the soda. Because if this is open to the atmosphere, in a matter of hours, most likely, it'll go flat. There will be some CO2 in there, but it won't be fizzy, because what we perceive the fizzy, the bubbliness of soda, is the excess carbon dioxide. So those soda stream machines where you can make your own soda at home, they use pressurized CO2. You can make any aqueous thing carbonated if you've got the right kind of CO2. Well, you have to have pressurized CO2. You can't just breathe on it. There's CO2 in your breath, but that's not going to work. So how does pressure change the solubility? Here we have a liquid, say water and carbon dioxide. The carbon dioxide will escape from the water, and it will also dissolve in the water. It will come to an equilibrium, and so we'll have a certain pressure of CO2 above that. If we increase that pressure by decreasing the volume, pushing down on it, we increase the concentration of the CO2. That's going to cause the rate of dissolving to go faster, because the rate of dissolving depends on this concentration. The rate of it leaving solution will remain the same. So after this process comes to equilibrium, we're going to end up with more CO2 dissolved than previously. I used to see advertised on TV these little gadgets you could put on your 2-liter bottle of soda and pump it full of air, pressurize it with air. That's supposed to keep it from going flat. The problem with that is the solubility of CO2 in water depends on the pressure of CO2. It's not just any old pressure. And if you're pumping it full of air, air is mostly nitrogen and oxygen. Very little CO2. It's like 0.6%. So that's not really going to do any good in terms of keeping your soda from going flat. This doesn't work.
So back then, we used carbon dioxide and then put the cubes inside the liquid. They used to keep the cubes in the freezer, right? Like to make soda? In the old days?
I don't know how they made soda in the old days.
Yeah, 'cause they used
That's
to
an
keep,
excellent
like,
question.
cubes of ice. I don't know if it was ice. I think it was like,
Well, dry ice is solid carbon dioxide.
and they would put
And
the-
I'm certain that you could make a carbonated beverage somehow that way. That would be another thing to look up in my free time. How did they make soda? I'm sure there is a video. There's a video of everything, right? There is a video about making things. There's a video on how to replace the heating element in the particular dryer that I have at home. I know, because we've done that like 4 times now. It's working currently. We're very happy. Okay, we can quantify the effect of pressure on gas solubility. So that's called Henry's law. The solubility of a gas, usually expressed in moles per liter, is equal to a constant, the Henry's law constant, times the partial pressure of the gas. That's usually in atmospheres. KH, the Henry's law constant, is going to be different for different gases, and it's going to be different for different solvents and for different temperatures. And so usually you'll find a table like this, and this is giving for different gases in water at room temperature. So this, again, is not something you would memorize, but this is the constant. And so to find the solubility, you just take the Henry's law constant for the gas you're interested in and multiply by the partial pressure of the gas above the liquid. So let's do an example of that. Determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. So we've got air at 1 atmosphere, that's just like regular old air. Air is about 21% oxygen. So then the partial pressure of oxygen is 21% of the 1 atmosphere, or 0.21 atmospheres. So we need Henry's law constant for oxygen. So there it is. The units are molarity per atmosphere, 1.3 times 10 to the minus third. So let's write that down. KH equals 1.3 times 10 to the minus third molarity per atmosphere. We're supposed to determine the solubility. The temperature, we need to know what temperature it is so we can choose an appropriate constant, but the temperature doesn't come into the equation. The solubility of oxygen is going to equal the Henry's law constant times the partial pressure of oxygen. So 1.3 times 10 to the minus third molarity per atmosphere times the pressure, 0.21 atmospheres. And so the atmospheres cancel out, leaving us with molarity, 1.3 times 10 to the minus third times 0.21. 1, 2, 3, 4. 2.73 times 10 to the minus fourth molar. Sig figs would be 2. So 2.7 times 10 to the minus 4 moles per liter is the solubility of oxygen at room temperature. Any questions?
So what would you do with that? So I look at that. Should I feel like that's soluble? Or
Well, water is soluble. Oxygen is soluble in water, but there's not a lot of dissolved oxygen in water.
Will you take in consideration the temperature? Would that affect solubility?
The temperature does affect solubility, and the way the temperature comes into this is when you're finding the Henry's law constant. These are all for a temperature of 25 degrees. So if you were going to say, let's look at it at 50 degrees, you'd have to find the Henry's law constant for oxygen at 50 degrees. Or if you were looking at freezing, or 1 degree Celsius or something, you'd have to find a different constant. That's where the temperature comes in.
So like bigger number, more soluble, and a smaller number, more soluble.
Oops. So if Henry's law constant is larger, then the gas is more soluble. And you notice that the solubility of ammonia is actually 58 moles per liter per atmosphere. And so that's much higher than the other gases. Another thing you can do at home, there's lots of do-at-home things. So take some water just straight out of the tap and heat it on the stove and watch it. It's easier actually in lab with a beaker, right? As you heat the water, and you may have noticed this when we heated water earlier, you'll see these little tiny bubbles. You're like, oh, it's boiling already. And then it's like, oh, no, it stopped. Those little tiny bubbles are not the water boiling. It's dissolved air leaving the water.